Write the names of the following ionic compounds. MgCl2. It would be magnesium chloride. We don't have to worry about dichloride or anything like that because it's an ionic compound, and we rarely worry about dichloride and things like that with ionic compounds. So KHSO4, it would be potassium at the front, then hydrogen, and then this bit is sulfate. So it's potassium, hydrogen, sulfate. Very simple. Okay, this one, Fe2O3 with this dot water thing here. Well, it's iron 3 oxide and 3 water. You've got, basically, it's just iron oxide with water ingrained in it. Okay. So write the balanced chemical equation for the reaction between aluminium and oxygen. Okay. So number one, we got to determine the product. What are we getting out from this reaction? Well, to do that, we need to know the valencies. So if you look up your periodic table, you'll see aluminium has a valency of 3+, and oxygen has 2- valency. We take the lowest common multiple, and that's 6. So you get 2 times 3 is 6, and 3 times 2 is 6. So therefore, we need 2 times 3 means 2 Al atoms, and 3 O atoms per molecule or unit. So then our final product is Al2O3. We write down the reactants, and on the product side, the ions that they form. So Al plus O2 gives you the Al3+ ion, 2 O2- ions, because there's 2 oxygens here because oxygen exists as a diatomic gas. Then we balance the charges on both sides. Now we're not going to use this equation right now because this is not actually going to help us. This is just a way to just understand what ions we're getting. So what we're going to do is we're going to say that there's going to be 3 O2- ions, because we need 3. And we need 2 Al3+ ions. And you can see that that's balanced, right? Because they're going to combine together to give us exactly that. Then the only thing we really have to do is balance the left-hand side. So here we go. So here we've got the same thing, as you can see, because we want to form this. And all we have to do on this side is just simply balance this side. So we've got 2 Al on this side. So we multiply this by 2. And you get 2 Al on this side. Then the next step is probably the one that people don't like the most. You've got 3 O's on this side. You've got 2 O's on this side. So how do you get 3 out of 2? Well, you just multiply by 3 on 2. 3 on 2 times 2 is 3, and that's your answer. Now that sounds a bit like a cop-out. How do you have 1.5 oxygen molecules? Well, it's not 3.5 oxygen molecules. It's 3.5 oxygen moles. And a mole can be split into any decimal that you want. I can have 10% of a mole. I can have 1.5% of a mole. So you can see that that number at the front is all about moles. So you don't have to worry that it's a fraction at this point. And that's our chemical equation. And so the final chemical equation is 2Al plus 3 on 2O2, which gives us this, and then eventually gives us Al2O3. Question 8. How can the Lewis dot diagram be useful in writing chemical equations? Well, the Lewis dot diagram is a visual representation of the valence shell of an atom. So it's a good way of visualizing what the outer shell of an atom looks like. And that can help in understanding the valency of the atom and the electron transfer process in the reaction step. So by knowing the valence shell, we can actually sort of understand where the electrons are going, which will help us write out the equation and get the valencies right, and also the charges of the ions correct, which will also allow us to get the final answer correct as well. Ultimately, the Lewis dot diagram is a visual tool to assist in the formation of chemical equations, and that's the whole point. It's just a visual way of understanding what's happening in this microscopic process. Question 9. I've been using this word lowest common multiple for a while, and you probably have seen it in your earlier studies of maths. And you might be wondering, well, why do we even need it in the first place? Okay, and I haven't explained what the physical meaning of the lowest common multiple is in this case. But the lowest common multiple is needed to ensure the final product, the charge of the final product is 0. As I mentioned in your chemical formulae lesson, that in a chemical, the charge of that chemical compound has to be 0. By using the lowest common multiple, we're actually forcing the product to have a 0 net charge, and that's important. So by using the lowest common multiple, you ensure the positive charges equal the negative charges, so that when you add it together, the net charge is 0. So in the case of aluminium and oxygen, the lowest common multiple was 6, remember, from the previous question? And so I need 2 Al atoms and 3 O2 minus to get the same lowest common multiple. But you can see that if I multiply these two together, it's plus 6. If I multiply these two together, it's negative 6. And if you add them together, what do you get? 0. And if you try and do that for any other chemical, just work with the lowest common multiple, then you'll get the same thing. That's why we use the lowest common multiple, simply because we want to force the net charge to be 0. Question 10. Write the balanced equation for the reaction between zinc and chlorine. As we always do, we determine the product first. So what do we actually get out of this reaction? But you should remember that from your valence tables. But we can find this one. Cl is -1 if you look on your periodic table. The lowest common multiple is 2. We need 1 zinc atom and 2 Cl atoms per molecule of this new product. And so we get zinc chloride, which is ZnCl2. So we keep that in memory for a second. Write down the reactants and on the product side the ions that they form. So we have it. Zinc turns into the 2+ ion and chlorine turns into the chloride 1- ion. And there's 2 of them because chlorine exists as a diatomic gas. And so there's 2 ions on this side. And then we balance the charges on both sides. Just by sheer luck, we've happened to got 2+, 2-, and so it's already all balanced. So all we have to do is just put them together, and then that's the end of our question. You know, it doesn't happen all the time like this, but it does happen frequently enough that you don't have to worry about that. So sometimes you'll get nice equations that you don't need to balance yourself. Okay, and that's just the beauty of chemistry sometimes. So that concludes today's lesson on writing chemical equations for ionic reactions. We looked at what are the steps to actually work out these chemical equations and how do we actually write them down. Okay?